This is lesson 2. Today we're going to look at multiplying and dividing radical expressions. We want to talk about getting simplest form when we're dealing with operations on radical expressions. Let's take a look at an example. Let's say we had the square root of 48, and we can simplify the square root of 48 by breaking down the 48 into a perfect square, 16, times its factor 3. So if you think about the square root of 16 separately from the square root of 3, you'll see that the square root of 16 is 4, and then the square root of 3 can't be simplified. So simplifying or getting simplest radical form from the square root of 48, we arrive at 4 square roots of 3. Then when we rewrite a denominator, let's say we had an example where we had 2 divided by the square root of 3. We want to rationalize the denominator. So we're going to see rationalizing the denominator. And to rationalize a denominator, you want to create a perfect square in the denominator so that your end result has no radical in the denominator. Here we have 2 times the square root of 3, and then combining the square root of 3 times the square root of 3 gives us the square root of 9. So our simplest radical form by clearing the denominator of all radicals would be 2 square roots of 3 divided by 3. Our properties for combining radical expressions: when we have a product, that would look like the nth root of a number times the nth root of a different number, and to combine them with multiplication, that would be the nth root of the product, a times b. And then the quotient rule would be the nth root of a divided by the nth root of b. And we are allowed to combine under the radical a divided by b, and then finally take the nth root when we're finished. So let's start by looking at example 1. Can you simplify the product of the radical expression? And if so, explain why or why not. So here I have the 4th root of square root of 7, or the 4th root of 7 times the 5th root of 7. And we would have to say in this case, no, we cannot simplify it because there are different indices on both of the radical expressions. So when we have a different index for each radical expression, they cannot be simplified. And you might want to make a note of that. No, we have different index for each radical expression. And I'll make a little note that the indices must be the same. Indices must be the same. So in this example, I've got an index of 5 and an index of 4, and those cannot be simplified. In part B, we have a 5th root of negative 5 times the 5th root of negative 2. So yes, we can combine those. And since they're both the 5th root, we would just multiply negative 5 times negative 2 and use that property. And our end result would be the 5th root of 10, and that cannot be simplified any further. Then finally in part C, we have the square root of 3 times the square root of negative 4. And we have a little problem there because the square root of negative 4 is not real. So we're being asked to simplify over the set of real numbers. And by simplifying, we would end up with the square root of negative 12. That can't be simplified without using complex number rules. So in that case, in this lesson, we would have to say no. So we would need the complex numbers in order to simplify, because the square root of -1 has a definition of I, and that's outside the realm of this lesson. So for this lesson alone, according to our constraints of just real numbers, we would have to say no. For example 2, we're going to give these a try. First, breaking apart the square root of 96, we could say that the square root of 96 could be factored as sets of even numbers because our index is 2. So I'm going to break apart the 5th power of y as y to the 4th times y. And then the square root of 16 is 4. So that's out from the radical. The square root of 8 would be x to the 2nd. I'm sorry, that would be x to the 8th divided by 2. So we would end up with x to the 4th. And then y to the 4th square root would be 4 divided by 2. So that's y to the 2nd. And under our radical, we would have 6 times y. So 4x to the 4th, y squared, times the square root of 6y. In part B, it's a cube root, which allows us to have a cube of a negative number. So I could think about this as -64 times +2 times b to the 6 times b. Remember, I want to have a power on my variables that are divisible by the index, and my index is 3, so 6 divides 3, or 3 divides 6 evenly, and 4 cubed is 64, so we have a perfect cube there. Then simplifying, we're going to get -4, and 6 divided by 3 would be b squared, and these two are outside of the radical, and I've got the cube root of 2b on the inside. So we have -4b squared times the cube root of 2b. And then part C, if you want to turn the video off and try this on your own, you can come back and check your work when you're finished. I'm going to reduce 72 as a factor of 36 times 2. And then we have x to the 4th and y to the 6th. Those are both even. So 6 is the square root of 36. And x to the 4th is x squared. And the square root of y to the 6th would be y cubed. This is an odd answer on an even index. And this piece of y cubed, this piece needs to have absolute value bars. With our rule from the last lesson, we have an even index and an odd power. You want the principal square root because it's the symbol for principal square root. So we're going to place some absolute value bars around y cubed to force that to be the positive answer, or the principal square root. So this one had its own little rule to follow. In part 3, we're doing the same thing. We have 45 times 35. So putting those together, we could think about 45 as 9, which is a perfect square, times 5. And then 35 can be 5 times 7. And combining like terms with x to the 5th times x. And y to the 3rd times y to the 4th is going to be y to the 7th, but I want perfect squares to help me simplify completely. Here, the square root of 9 is 3. I've got a pair of 5, so the square root of 25 is 5. It's the square root. X to the 6 is x cubed, and y to the 6 is y cubed. And then left behind would be 7 times y. Now here's where we have the issue with the odd power, the principal square root. We want to force that to be a positive answer. And x or y could possibly be a negative from the beginning. So we want to force that to be a positive answer, we've got xy quantity cubed and the square root of 7y, which follows our rules for simplifying radicals. In part B, it's a cube root. And cube roots, we're going to think about the cube root of -2 times 16. So let's think about that as, let's see, we've got a -1 and a 2, and 16 can be 8 times 2. And then m to the 4th times m cubed is going to give us m to the 7th, but we're going to write that in multiples of 3. And n to the 1st times n to the 5th is n to the 6th. So here the cube root of -1 is -1, and the cube root of 8 is 2, so I'm going to pull out a -2 there. The cube root of m to the 6th is m squared, and the cube root of n to the 6th is n squared, and what we have left behind is the cube root of 4m. So this, I guess you can just either leave it this way or combine the m and the n and write that as mn quantity squared if you would rather write it that way. Either way is acceptable. Then part C, we have a square root. So we've got -3, and then 18 times 2, that product is a perfect square, 36. And x cubed times x to the 5th is x to the 8th. And then combining like terms will give us y to the 10th. So here we have -3 times the square root of 36, and x to the 8th square root is x to the 4th, and y to the 10th square root is y to the 5th. So in this case, we're going to need the absolute value bars on y to the 5th, since that's an odd power with an even index. And our final answer would look like -18x to the 4th times the absolute value of y to the 5th. In example 4, we're moving on to simplified form for quotients. And I want to practice with getting the radical as one radical of a division problem. So we've got 50x to the 6th divided by 2x to the 4th, which is going to simplify down to 25x to the 2nd. And both of these are perfect squares, so we're going to end up with a final result for a principal square root of 5 times the absolute value of x. In example B, combining those two radicals into one radical, 45x to the 8th divided by 5x squared can be simplified as 5 dividing 45 9 times, and x to the 8th over x to the 2nd is x to the 6th. And this could simplify down to the square x squared, and the cube root of 9 cannot be simplified, so that's got to remain behind under the radical, and we have x squared times the cube root of 9. Again, on part C, if you want to give this one a try on your own and then come back to check your work, I'll be right here to walk you through it to make sure you've done everything correctly. So 81 x to the 5th, y to the 11th, divided by 16x cubed, y cubed, can be simplified down to the cube root of, or the 4th root of 81 would be 3. And then we have, let's see, x to the 5th over x cubed, that would leave us x squared. And y to the 11th over y cubed would leave us y to the 8th. And on the denominator, the fourth root of 16 is 2. So we're still thinking about this. Then the fourth root of y to the 8th would be y squared. And we're going to leave the fourth root of x squared under the radical and divide that by 2. Now, if you wanted to, you could also write that as 3 over 2 y squared times the fourth root of x squared. That's just a personal preference. Okay, for example 5, we're going to practice rationalizing the denominator. First, simplifying 5 over 20, that would be 1/4. And x squared with x cubed on the bottom would leave us an x on the bottom. So we want to rationalize this, and I need to get a perfect square in the denominator, so I need another x in both the top and the bottom. So I need to multiply some radical that's in the form of a 1. Here that gives us x under the radical in the numerator, and it gives us the radical 4x squared in the denominator. So we have the square root of x divided by 2 times the absolute value of x. Remember, this is the principal square root. In part B, we have the cube root of 7x, and we have the cube root of 5y squared. So I want to think about this one right here. To get a perfect square, I need 2 more 5's and 1 more y. So if we multiplied the bottom by 25y, we could also multiply the top by 25y. That would give us that perfect square for both the denominator to rationalize that denominator. So 25y in the numerator and 25y in the denominator. That'll give us and that needs to be the cube root. So we've got the cube root of 25 times 7. That's 175xy under the cube root. And in the bottom, we've got the cube root of 125y cubed. That's 125y cubed can be thought of as 5y quantity cubed. So this is a perfect cube here, and our numerator is going to remain the same, the cube root of 175xy divided by 5y. No need for absolute value bars because my index was a 3. Do you think you can tackle part C all on your own? Come back and give it a try. We've got 15 divided by 3. That's already a 5. So we want to simplify first. And if you think about 12 and 60, we could say that that's the square root of 5. And then x to the 5th divided by x. That would give us x to the 4th. And y cubed in the numerator divided by y to the 4th in the denominator, that would give us the square root of y in the bottom. So we want a perfect square in the bottom to rationalize. That would be the square root of y. Whatever you do to the bottom, you do to the top. And that's going to give us 5 times, let's see, we got the square root of x to the 4th, so we could go ahead and simplify that. That would be x squared. And then the 5 is going to stay behind, and the y is going to stay behind since we took that square root. And we got the square root of y squared on the bottom when we combine these two terms. So the square root of y squared would give us just a y in the denominator. And it's a square root, so we need absolute value of y to force that principal square root. And we got that done. Now on to some problem-solving word problems. Here we have the formula T is 2s divided by a. That shows the time a vehicle will travel some distance s at a constant acceleration a starting from rest. We want to know what the difference in the time between a car accelerating at 16 meters per second squared and one accelerating at 25 meters per second squared for a total distance of 200 meters. So our value for s, we've got the square root of 2 times s. S is 200 meters. And the acceleration here is 16 meters per second, 16 meters per second squared. So this looks like we have a numerator. We can cancel out the meters over meters, and that's going to give us the square root of 400 divided by 16, and then 1 over seconds squared becomes seconds squared in the numerator. So here we have time is the square root of 400 divided by 16. So that turns out to be 25 s squared. And that's a perfect square. So we have 5 seconds for a car to travel at 16 meters per second for at that rate for 200 meters. And then for the last one, what's the time that a car accelerating at 25 meters per second squared takes to travel? It's our same formula. So shows the time is the square root of 2 times s, and s is the distance. So we're still traveling 200 meters divided by 25 meters per second, and the meters will cancel. The second squared will come up to the numerator when we simplify that. So we're going to get 2 times 200 seconds squared over 25, and 25 divides 400 16 times, so 16 seconds squared under our radical. So in this case, our time is 4 seconds that the vehicle takes to stop at 25 meters per second. And that, my friends, is the end of lesson 2.